You're back today?
I'm back.
The Aggies won, so that was great news. So we had two of our students go to the Final Four, so they are back now. So you guys had fun?
Oh, it's a great time.
Great time. Huh? That's good. Any questions before we get started? We're going to finish up the case study on the HVAC system today. But before we go there, I just wanted to remind everybody to keep working on the project. And we're going to talk more about the individual projects next week. I will ask you to give me an update. So each team is going to talk about what they have done so far, where they are, to make sure everybody's making progress. So I didn't assign any homework this week, and I may not assign homework next week. I have 2 homeworks left. But I want you to kind of make headway on the project, and then we're going to do some new stuff, and then I'll assign the homework. Okay? So let's go to the slides. I think we stopped somewhere here. We're discussing the class diagram. Any questions on class diagrams in general? Mm-hmm. Yes.
So we have some headings that we have to discuss in use case, right?
Yes. For the use case documentation.
Yes.
Mm-hmm.
But in some of the reports that we saw,
Yes.
previous students have done, they have not discussed each and every heading. So
Yeah.
are you supposed to discuss everything, or just include something which is relevant to?
You have to include whatever is relevant to your system. But in general, you should try to fill in the blanks as much as you can. So whatever is relevant to your system. Yeah. The question is about the use case documentation that we looked at. We're going to look at more of it even today. We have those slots where we have to put information. The question is whether we should make sure we fill in all the blanks. And the answer is, depending on your system, yes, you should try to fill in all the blanks. But if something is not relevant to your system, then you can leave it blank. Okay. So we're looking at so far we have come up with this class diagram. We have discovered that we need to have a thermostat, which is going to be sensing the temperature, and also providing information when the temperature goes above the thresholds for heating, and there's a threshold for cooling. We also identified a controller, which is going to receive that information from the thermostat, and the controller is going to actually control the turning on and off of the air conditioner, the heater, and also we added a fan. Okay, so far that's what we have developed. The next thing now is to look at the other parts of the analysis model according to the this unified modeling process or system development process. So here's a discussion about looking at alternatives. In other words, we are trying to come up with an incipient architecture for the system. And these are some of the the things we have to look at. What's the candidate architecture for the system? What are some of the alternatives we can look at? Also, we have to look at glossary basically refers to when you're developing a system, you are also going to be developing the terminology you're going to use. So you have to develop description or definition of the terminologies you're using. Risk analysis, what are some of the issues that can happen? Okay, let's try this one more time. Okay, so we are going to look at the candidate architecture, the so-called piggyback system for the HVAC system. And if you've lived in Arizona, you probably know what this refers to. But if you haven't, here's a discussion or description about other things we have to look at. So they performed some type of risk analysis, and they found out that the AC air conditioning actually might cost as much as $7 per day. Okay? And then they concluded that this may be too much, especially for graduate students, if they are going to live in the house. This is coming from maybe the homeowner. And so they proposed to have what is known as a piggyback system. And basically, the piggyback system involves using an evaporative cooler during certain times of the year. Instead of using the AC, because the AC is more expensive, you can use an evaporative cooler, which is cheaper to run. But it is not as efficient as the AC in terms of cooling. So in Tucson, in particular, in March, it's nice there during March, April, and sometimes May. So on March 21st, the homeowner turns the heater off and the evaporative cooler on. So they plan to use the evaporative cooler from March up to June. June, it's pretty hot there. So for between March and June, Tucson is usually very dry, but it's not as hot. So maybe during that time, they can actually turn on the evaporative cooler. So then after that, when summer comes, then they can turn off the evaporative cooler and the air conditioner on. July and August are the monsoon season in Arizona. It is humid, and the evaporative cooler doesn't work well. So then during that time, the evaporative cooler can be turned off. Okay, and then September 21st, the homeowner turns off the air conditioner and the evaporative cooler on. So September to November is also a nice time. It's not as hot. So the piggyback system is going to allow to switch from the AC to the evaporative cooler. So this is an idea that they looked at after doing their risk analysis. Question? In August, it usually doesn't work well. Here, it is humid and the evaporative cooler does work well, so we use does not. Yeah, so we use the air conditioner. So this does not work well. Okay? So the evaporative cooler doesn't work well in, so August, September is pretty hot. Question?
So in terms of the timeline, when we're doing the risk analysis, and is when we find out that, or it was before that we came out to find out, oh, it's too expensive, we should look at other alternatives?
Some of it was probably known ahead of time when you do the needs analysis.
So this is not an outcome of the risk analysis per se?
No. This one, they did it after they finished the needs analysis. So they started looking at this analysis model. So far they have identified the AC and the heater. And then, they looked around and found out that actually the AC is expensive to run. So they started thinking about an alternative design. That's why they are talking about maybe we can add an evaporative cooler. Okay. Any other questions? Okay, so let's move on with, so now we're going to have an evaporative cooler added to the system. Okay, and we're going through this analysis. We're trying to design the system. So we're going to start looking at the design model. Again, if you look at their development process, this is about this. They're going through this the second iteration. That's when they are trying to basically add more information or add more meat to the whole system. And they're going to add more use cases because now we're going to have this evaporative cooler, which we have to turn on at specific times and turn it off at specific times. Okay, and then of course we're gonna improve our classes. So now we have to accommodate this new piggyback system. So going back to the use cases, we have the cool house use case. This is the same as before. Okay. Then we also had the heat house use case, and this one is the same as before. Continuing on with the heat house use case, we saw this before. Okay, so this is continuing on. Then we also had the display system status use case. So the system shall monitor the health of each object in the system and display the status of the complete system. They have added that this display should indicate ready or fault. So if something is wrong with the system, then the display should say that. Also, in addition, I think we also mentioned that the system status shall be computed periodically. For example, you can compute it every minute. Okay, so it's discrete time every minute. Or they are saying it may be event-driven. So when we talk about discrete events, the event has to trigger the computation of the system status. So again, I plan to talk about discrete event in the next week or so. So an event could be, for example, when you have a state transition. Okay. So, for example, if you turn one of the components on or off, that could be an event, and that can trigger computation of the system status. Okay. So event-driven systems are good for cases where you don't have to know the state of the system every second or every minute. You only want to know what's going on when there's a change in the state of one of the components. Okay. So then they want the system to display the system status continuously. So the system status can be displayed continuously, but the actual computation of the system status can be done at specific time intervals, or it can be done when there's an event. They give an example of a success scenario where they have the fan interface executing a built-in test and then reporting back to the controller. The air conditioner does the same, reports back to the controller. The evaporative cooler, now we have added the evaporative cooler. They also wanted to have a built-in system test. And it also has to report to the controller. Same thing with the heater. The thermostat as well. So they're adding more stuff now. Then once the controller gets information from all these components, then it computes what the system status ought to be. Okay? Obviously, if one of the components fails, then it may say that this particular component is not working, so the system is not ready. Then the controller sends the system status to the thermostat. So it looks like they want the thermostat to actually have the display. So they want the thermostat to display the system status. And then the homeowner can actually go to this thermostat and observe the system status periodically. Okay? This is, did we discuss this use case, or this one is new now? This one is the new use case. We've talked about setting the temperature, right? So we need to add this use case as well. So this is set temperature limits use case. So the homeowner changes the temperature limit. Remember, we have the limit for heating. We also have the limits or thresholds for cooling. So we need to have this use case as well in our system. So this is going to be a function that has to be performed. And so they give a precondition here that the homeowner has selected the equipment. So now we have something that the homeowner has to do. So there's this idea of selecting the equipment because we now have a piggyback system. So we may have the, depending on the time of the year, we may use the evaporative cooler or we may use the AC. So there's this function that has to be performed that is selecting the equipment. Okay, so we're going to have another use case for that, a use case for that. So here is an example of a success scenario. The homeowner sets cooler upper limit. The homeowner sets the lower limit for cooling. Then does the same thing for the heating. And then that ends this set temperature use case. So we have added another use case for setting the temperature by the owner. And then this one is the selecting equipment use case. It says configure equipment. The homeowner chooses which equipment to turn on, the heater, air conditioner, or evaporative cooler. Why is this needed? It's added. What's the added value? It's necessary for operation and maintenance. I think early on we said that the homeowner has to perform the maintenance on the system. So that's why we need this use case, configure equipment. So the homeowner has to select which equipment to turn on or off in case they have to perform some maintenance. Assumption, if the homeowner wants heating and cooling on the same day, then he or she will switch back and forth manually. So they give you that option to switch manually. Okay, and then they provide, again, this information, the primary actors, the homeowner, the frequency, how often you do this, the system status has to be ready in order to do this. A success scenario, homeowner turns heater off. This is in March. This is when you usually want to turn on the evaporative cooler. Then June 21st, homeowner turns the evaporative cooler off and the air conditioner on. Then after September, then you turn on the evaporative cooler. Post condition, one of the three systems is active, so one of the systems has to be working after you do this. So now the design model use case diagram looks like this. Okay, so before we did not have some of these use cases like set temperature limits. We also did not have this one, the configure equipment or select equipment. Okay, so now we can see that the homeowner or the user can actually interact with the different components in the system via these use cases, heat house, set temperature limits. Again, this one is one of those use cases that doesn't interact directly with any of these components. Okay, but it's going to interact with what's going to be inside this HVAC system. Okay, and like we discussed last time, we have to look at the documentation to understand what these set temperature limits mean. Okay, we have to look at the documentation. That's why we have to write how we think this should work. Cool house is going to interact with the evaporative cooler now. So we're going to have the evaporative cooler, air conditioner. Then here we have select equipment. We can choose equipment. Then display system status. Something is missing in this diagram. What is missing? Eric?
Whoever the person that fixes or the system or does anything to the system besides the homeowner, let's say the repair person.
Yeah, they are just assuming the homeowner is going to do the repairs, but yeah, if you want somebody else to repair the system, then we can add another actor who can do that. What's missing? The thermostat. Do we need to add the thermostat here?
Like to cut off the AC, the temperature switch.
Yeah, so the basically in terms of the use case for the thermostat, that is kind of inherent in this whole thing, the HVAC thing, but it's not shown here. So that's missing here. It's not shown. The thermostat is an object. Right, just like we put the heater, we can add the thermostat there. Another thing that's missing, the fan is missing. Remember we said we need to have a fan as well? So again, I'm just showing you this. We can update this picture. We need to add the fan here. So the thermostat, the thermostat is the sensor.
In terms of the thermostat, if we didn't have the thermostat in this specific use case, would the use case still be good because you're having the action of set temperature limits without having the thermostat?
This is the answer is no, because this use case diagram is showing the homeowner, how the homeowner interacts with the system. Okay, so by just saying having this set temperature limits in our description, we have said that we are going to actually use a thermostat to do that. So this is basically showing how the homeowner is going to interact with the system. But what's missing is what this use case is going to interact with. And we are saying that this basically is going to interact with the thermostat. So we can show the thermostat in the picture. That's missing as well. Okay, so my point is this is not complete. This is not a complete use case diagram. So there are things we need to add here to make it complete. Okay. Anything else? Okay, so let's look at an example of a sequence diagram. Now the thermostat shows up. Okay, so here's a sequence diagram. So we have these objects. So we have a thermostat. We have a controller. And then we have the heater interface and then the heater. So we're just showing, again, sequence diagrams are going to capture scenarios. Okay, so they will capture certain scenarios. And therefore, you may not have all the objects or entities in your system shown in a sequence diagram. It will depend on what scenario you choose or what you want to portray. In this particular case, they are trying to portray the interaction among these entities, the thermostat, the controller, the heater interface, and the heater itself. So time goes this way for the sequence diagram. Some of you had questions regarding, how long should this be? Typically, we don't care how long this is. We're just basically saying there's a time interval. There's going to be some elapsed time. However, if you knew the exact time, then you can actually put these according to the time you're going to have. But the software we are using doesn't actually allow you to enter, the time on along this axis. So here we start with the thermostat. The thermostat is sensing the temperature in the house. and the room temperature is has fallen below the heater lower limit. So it sends a signal to the controller. The controller gets that signal. It's going to take some finite amount of time to process the signal. Then it's going to send a signal to the heater interface saying that the temperature is basically below the heater lower limit, so we have to turn on the heater. So it sends a signal to the interface. The signal takes some time here and then finally goes on to the heater to turn it on. So the heater is on. Then some time later, going down, so some time later, so this amount of time has elapsed, has gone by. The room temperature now is above or equal to the heater upper limit. If this happens, if the temperature goes above, then the thermostat is going to send a signal to the controller saying the temperature is above the upper threshold, and then the controller is going to send a signal to turn off the heater. So the signal goes through the interface, then from the interface it goes to the heater to turn it off. Okay? You can see in this particular sequence diagram there is no feedback. Since this is just more like a one-way signal. Many complex systems, you want to have a confirmation if the signal actually was, reached the destination. So you want the feedback. So you will see some sequence diagrams having feedbacks. This one is pretty straightforward. Okay. This is the same sequence diagram, but now we have added the homeowner. Okay, so we have added this entity, and the system itself is working. The HVAC system is going to be working autonomously, and so we have this going on. We turn on the heater when the room temperature is below the heater lower limit. Then in this case, we have the homeowner, smells gas. So the homeowner now actually goes to the controller because there is a use case where they can actually configure the equipment, so they can turn on whatever they want. So now the homeowner actually goes to the controller to turn off the heater. So the controller sends the turn off signal to the heater via the heater interface. And so the heater is off now. So this is another scenario that can happen. Smells gas is the homeowner is in the house. Remember in one of the scenarios they described that the homeowner there may be a scenario where the homeowner can smell gas in the house. So if you smell gas in the house, it's not a good thing if you have the heater on or you have, the fire on or stove on or anything. So for safety, you want to turn it off. Okay, so they're just showing this as something that can happen. Okay. This one, the use case?
Yes.
Mm-hmm.
You think that when you have an arrow there, so that's one-way interaction, right?
For this one?
Yes.
This one shows the direction of interaction. So it's the homeowner which is going to actually initiate this interaction. So that's why it goes from here to here.
And what about from heat house to
So
heater?
the heater by itself is just going to wait for some signal to come to it. The heater is not going to decide to send something back. That's what this is saying. Okay?
Heater heats the house, right?
Yeah, it does heat the house.
So will it be other way around?
No. So, okay, I see your point. So the question is, should we have this arrow pointing back because the heater is going to heat the house? No, this is a use case diagram. We are looking at the interaction. So when we have a use case, we are basically portraying the function that the system is going to perform. This is the function that's going to add value to the system. in this case to the homeowner. So the homeowner is going to initiate basically this interaction from here to this use case. Then from the heat house use case, this system is going to basically send a signal to the heater. And then the heater has to do whatever it has to do. So we don't look back at what the heater is going to do as feeding back to the use case itself. Okay? All right. So going back to, I think, the sequence diagram. Any other questions on the use case? Okay. So now let's look at the design model for the class diagram. So now this is a more improved class diagram from the previous one we looked at, because we are going through iterations, and now we have added this piggyback system. So we have a thermostat. So a thermostat is going to be represented as it's an object, and it can be represented as a class. And so the thermostat is going to have attributes. These are the attributes or parameters, the thresholds. And also the thermostat is going to be sensing the room temperature. So we have to have a room temperature value, which can be represented as an integer. Okay, if you're going to implement this as a simulation. Then these are the functions or methods that the thermostat is going to perform, comparing the room temperature to the thresholds. The thermostat is required to do a built-in test. Also, the thermostat in this particular case should also display the system status. You can have a separate display unit, separate from the actual thermostat. But here they want it to be, together, the whole thing. The thermostat is a temperature sensor as well as a display in this case. And then the homeowner is going to be interacting with the thermostat. So that's how they interact with the whole system. It's going to be via this thermostat. Okay? And then there's a controller. So we're going to have some type of controller. The controller has this attribute, system status. They just want to indicate whether the system is ready or it's at fault in this particular case. Okay? And then the controller also has this built-in test, because it can request to get a built-in test from each component and compute the system status. And then the controller is going to interact with the AC interface, the evaporative cooler interface, the heater interface, and the fan interface. And each interface is actually connected to the actual component. So you can think of these actors here as, physical components. Okay? So the system is going to comprise all these entities, and then these objects are going to basically be tied to this system. So the system is going to be, this HVAC system includes these, but these are just going to be working out there. So they'll be connected. They will be physical entities or components we can just buy off the shelf and add them to the system. Notice that there is, again, this is an association. This is a two-way association. There is no error, so which means information can flow back and forth. Why do we need information to flow back and forth over here? Okay, so the controller can tell the fan or the AC to turn on. We go this way. How about going back? The controller is going to know that. So the controller is going to know that, okay, I'm going to turn on the AC, so I should now also turn on the fan. So it goes one way. What about going backward? The reverse. Yeah, the built-in system tests. Okay, so when the interface here executes this built-in system test, it's going to check whether this component is actually working correctly or not. And then it's going to send back that information to the controller. That's why we have this type of association, two-way association. Okay. Any questions on this class diagram? Do we have any programmers in this class? Anybody does Java? Only one person? Nobody is doing programming these days? So we can actually take the class diagram. Again, this is from a software point of view, even though we are doing system design. But we can take this class diagram and the use cases and give them to a programmer, and they can actually program this. We have provided a specification for basically building a simulation model for this. Okay? So that's the cool thing about this system design process, where we actually use object-oriented analysis and UML. It allows us to come up with a model, design model, and we can actually take this information and build the software.
Is the only information that is coming back from the AC interface for the built-in test, or is also when it surpasses one of the thresholds telling it turn it off?
No, it's just the question is there any other information going back from, let's say, the fan interface to the controller? In this case, it's just the built-in test results that are going to go back. Okay, all the other information is going to come from the controller. The controller is going to get information, basically what's going on in the house in terms of the temperature from the thermostat, and then the controller is going to decide what to do. Yeah, so it's going to go one way from the controller to the interface. Okay, then from the interface, obviously, to the actual air conditioner, it's going to basically turn it on or off. Okay. State transition diagrams, we've done these a lot so far, so I don't need to say much here. This one is very simple. This is a state machine diagram or state chart. So in this case, they only captured, they call this the HVAC controller, but they only captured the heater and the I think this is the evaporative cooler. Yeah, so let me ask a question. In terms of the state machine diagram for the entire system, what should we have inside here? This particular state machine diagram is just showing the heater, and it's showing this cooler. Jonathan?
Does it not show the inputs for the HVAC controller? Are those like the two subsystems?
Yeah, so this one is just showing more of a subsystem. In order to look at the system state, when we say the system state, remember what we said before? We have to look at the Cartesian product of the states of each system, each component, each subsystem, everything. That would be a snapshot of what's happening, right? So for example, we can describe a state, a system state, as including whether the fan is on or off, the heater is on or off, evaporative cooler, the air conditioner. We can also look at the thermostat, what's the temperature in the house. That is going to be part of this, describing the system state. We can look at the controller, what the controller is doing now. In this case, they have only the system status, whether it's ready or at fault. So that entire combination is going to define a system state. Okay, so if we were to draw the state transition diagram for the whole system, it would be very big. And so typically we show state transition diagrams for maybe a component, maybe a subsystem, and so on. So when you start working on this for the system you are designing, that's when you're going to realize that it may be too difficult to actually portray the system state using one state transition diagram. Okay, so here they just show this. So let's go over this one. For the heater has two states. It can be on or it can be off. Same thing with the evaporative cooler. I believe that's what this is supposed to be. It's on or off. Now, when we draw these state charts and we want to show initialization of the system, remember the system is going to be off at some point, then you have to turn it on, then we have to define the initial state. Remember when we looked at the system experiment data tables, we had to specify the initial state. The modeler specifies the initial state. You are creating this system, so you're going to define what should be the initial state for the system. So to show that in a state chart, we usually use this black dot. So the black dot indicates, the system is not working or the system is not turned on. Then when you turn on the entire system, in this case the HVAC system is turned on, then what's going to happen to the heater? Initially the heater is going to go in the off state. Okay, same thing here, initialization takes you to the off state. So whenever you initialize the system, it is showing that these components are going to start in this off state. Okay? So if you were to basically build this system, you turn on your system, the first thing that's going to happen is these components are going to be off. Then the thermostat is going to start sensing the temperature. And depending on whether the temperature is within the thresholds for heating or cooling, it will decide which one should actually now go on or which one should actually stay off. Okay? So when you draw these state charts using IBM Rational Rows software, you're going to have this option of providing the initial point and pointing to the initial state. Okay? So in simulation, we just say initialization. When we say initialization, initialize the system, we're going to specify which states we're going to initialize, which state we're going to initialize the system in, or which state we're going to initialize each component or subsystem in. Okay? Any questions on state charts? Okay, so moving on with this example, they have given, so they did this and then they came up with a requirement that everything should be, this could have been given by the customer, but the homeowner is the customer in this case. So they want to have, to just buy these components. So they have to find the right components to fit their specifications. Okay, so in that case, you can actually start talking about this buildable system. Now you want to build the system. In this case, they call this the implementation. So this is what you can actually implement. So they give an example of a cooler, the specifications, the thermostat interface, and the cost, the schedule, the performance. Okay, so you're going to do this for each component in your system in this particular case. Okay, And for this particular system, I think we have proven technology for everything. So for our working definition, this is not a complex system. Okay? But for the project you are doing, we want to make it more interesting, so we have added this complex system where you can think outside the box and come up with something that you can dream about. Next, we move on to system testing. What is verification? We talked about this before. Verification means what? Verification means building the right system or building the system right. Verification means building the system right. So as you go on, you have to verify things. You have to check. You have to, and so on. Building the correct system is validation. This is when you have the actual system. Now you wanna compare with what you say the system has to do. Okay, the real thing. That's validation. If the real thing conforms to what you want, complies to what you want, you said it should do, then you have a validated system. Okay, so we do verification in order to build the system right. Of course, we eventually want to have the right system. And there are three common ways for doing this system testing. We have covered state-based testing already. And Behe also concluded that this is the best way to test a system. Remember the system experiment data tables? You have to run your system through all those possible states. And that, it's difficult in practice to go through all the possibilities that can happen to a system. So the issue is, how are you going to decide on whether you have enough, you have performed enough tests? And that's a hard problem. So state-based testing is the best way to go. Okay? And of course, for this particular system, we can actually maybe enumerate all possibilities. We can build a simulation and go through all of them maybe in hours or maybe days. But for more realistic or complex systems, it's not easy to do that. Because you may not experience certain inputs, combinations of inputs and combinations of states at certain times. You may not go through that. So the other ways to actually test the system is to use the test vectors. This is where you look at the input-output. You have the input, you know the output. So you can actually feed the system the input and see what the output is, and then compare with what you expect. The next one is the one I just mentioned. The other one is the scenario-based. This is where the use cases become handy. Remember we talked about main success scenario. We can use those to actually test the system. Okay? And here they give some examples. So let me go through these examples quickly. Using inputs and outputs, this is what they call the test vectors. So they suggest to go use the inputs where you have the normal inputs, what you expect. Look at the extremes, and also look at some incorrect inputs or mistakes to test your system. So the normal one is they give the heater upper limit and the lower limit according to the specifications. This is an extreme case where they give these limits very high, at high temperature, and then at low temperature. These are extremes. So you can set these and then run your system to see how the system is going to perform when you do your tests. Here's a mistake where the upper limit is less than the lower limit. So what should the system say here? The system should say that's an error, right? Because the homeowner is going to go try to set the thresholds, and then they put this as the upper limit for heating, and this as the lower limit. then the system should identify that this is a mistake. Okay? Continuing on with test vectors. So they provide an initial state. Here they're looking at the cooler. Could be the AC or the evaporative cooler. So they start with any state. They look at the event, which is the input. Remember, the input to the cooler is going to be coming from the controller. Where is the controller getting the input? The controller is getting the input from the thermostat. The thermostat is getting input from the temperature sensor. Where is the temperature sensor getting information from? From the ambient temperature in the house. Okay? So if the room temperature is greater than the cooler upper limit, then what should happen here? The cooler should be on. That's what's expected. Then if you are in a state cooler off, and then you have the room temperature below the cooler upper limit, means you are good, right? So you expect the cooler to be off. One more, the cooler is off, the room temperature is equal to this upper limit. In this case, you have reached the threshold, you want to turn it on, and so on. So the test vectors basically list the state you have and then the input and what you expect as the output. So when you run your system, then you can just compare what you are getting. Okay. So if you're not getting this, then it means that your system is not working correctly. Okay, so you have to go make some adjustments. Here's a procedure for testing the heater. Okay, this is what you can do in, I guess, in real life. Choose a cold day. Okay, e.g., outside temperature is less than 60 degrees Fahrenheit. That's very cold for Tucson, by the way. So you set the heater on or off, switch to on, then you set the heater upper limit and the lower limit according to whatever you have defined in your test vector. Then you observe the room temperature for 1 hour and see what happens, if the system is going to conform to what you've specified or not. Okay, if for example the temperature goes outside the heater limits, then something is wrong. So basically the test has failed. This is what you know already. Testing using system experiments, right? So you have the time zero, you provide the initial state, and then you have the inputs, and you can run through this. Okay, so this should be very familiar. Test using use case scenarios. So you can go back to your use cases and you can pick each one and define a test for each use case. So here's a scenario. So they start this scenario on this particular day. The outside temperature is 40 degrees. The heater is off. The system status is ready. The room temperature is 70.5 degrees. And they have set the thresholds at default values. And then they observe the room temperature falling below 70 degrees. Then they expect that the system should actually turn the heater on because this is the lower limit for heating. So this is what they see. The heater is on and the fan is on, so that's good. Then the heater starts to heat the house. Then they start seeing the room temperature rising. And then after reaching the upper limit, the system turns off the heater and the fan. Then for the next 15 minutes, The room temperature must remain greater than, So remember those cycles, so they wait and make sure that everything is working correctly. So this is an example of testing using a use case scenario. Okay, so I think we are done with this one. Let me just mention that we can take this information, this design, and actually build an operations model. Is something we can use for initial testing, and then before we actually build the real thing. So we can build a computer simulation. I'm trying to set up the simulation software on this machine. If I'm successful this Friday, then next week I may show you a simulation of the HVAC system. Okay, so you see in the simulation how everything is represented. It's a little bit different from this one, but you get the idea of how you can actually build from the design. What we have done, you can actually build the software. Then after you have your computer simulation, then you can now go on and build the real thing. Okay? Lastly, there are many other UML diagrams that I would like you to know. One of them is the activity diagram. So make sure you read those on your own. The deployment diagram, communication diagram, and so on. Read those on the internet so you can understand those, because you probably encounter some of those in future. Okay, so you should be familiar with most of the UML diagrams, if not all of them. Okay. Are there any questions regarding this case study? Okay, everybody is now ready to do the project. Okay, so we have about 4 weeks left, as I said in the email. So don't put it off. Last year, some students said they didn't have enough time. You guys are going to have enough time because I'm reminding you now. And so if you work hard on the project, you get good evaluations, because the project, for the most part, is going to be graded based on feedback from everybody. So we have more like a peer review. You're going to present, and everybody's going to provide feedback, and we're going to use that information to grade your project. But your report, the TA and myself are going to grade the report. So the report should have this information. So if you are missing something, you lose points. So make sure you are diligent with the use cases. All the documentation should be in the report. Okay. All right. So next week, we may go through another case study. I asked the TA to compile some slides for another case, a different case study. So we may do that, and then after that, we're going to start looking at some new material. And I'm trying to get somebody from industry to come and talk about IDEF and how they use them. So we may have somebody come in maybe 2 weeks from now. Okay, otherwise we're going to move on to the new material. We have the discrete event models to theoretical models. We're going to go through the math again. And then after the math, we're going to go through some examples and maybe even the software itself. And I'm going to post a couple slides, a couple lectures on the after you finish the concept definition, then you go on to advanced development. There's some issues that you should be aware of. So I'm going to post some lectures on what you need to be aware of in that case. Okay? All right. Have a good weekend.